All right, so good afternoon. I hope y'all are feeling good. I hope you enjoyed, if you didn't have to do any CASP testing today, being able to kind of sleep in and have the whole morning to yourself and be able to have breakfast and have coffee and relax a bit and maybe get caught up on some stuff, you know. I hope that you were able to use that time as you wanted to. We don't have a lot of time, so we're gonna get going. Today, what is going on with this thing? It's just being different. Okay. We're gonna do as much of a review as I can get through of everything that we've covered so far this year, all the chapters. It will not be entirely in depth on everything. I don't have time to do that. But it's going to hit on a lot of the main points, and if you need more than what this is going to provide, I suggest going back into the chapter modules from this semester or the resources from first semester to see more about these topics. All right. So let's get this going. Maybe it'll work better. We'll try. Go. Go. There we go. Alrighty, so here we go. If you have any questions as I'm going through this, please ask. I suggest watching and listening and only taking notes on things that you have forgotten completely and you're like, oh my god, I want to make sure I remember this. Jot those things down. By no means do I want you to try to copy everything that you're going to see today. It's going to go too fast for that. But if you do have a question and you need clarification on something that I've said or something that's on a screen, stop me and ask. All right. This is going to come fast. It's going to be kind of like drinking out of a fire hose. So we're going to do the best we can here. So here we go. A time to review what we have seen so far. All right, we covered some main topics. All right, Chapter 4, we did sampling and surveys and experiments. Chapter 1, how to describe and display categorical and quantitative data. Chapter 2 is percentiles, mean, median, range, IQR, standard deviation, density curves, and the normal distribution. Bunch of stuff in there. Chapter 5, we started working with probability, simulations, conditional probability, and independence. Chapter 6, which is the beginning of semester 2, we did discrete and continuous random variables, and we considered how to transform and combine random variables. We used the binomial random variables and geometric random variables when needed. Chapter 7 is sampling distributions of sample proportions and sample means. Chapter 8 was confidence intervals for estimating population proportions and population means. Chapter 9 was significance tests for testing claims about population proportions and population means. And lastly, the chapter we just finished, Chapter 10, comparing two populations or groups through confidence intervals or significance tests. So this is all the things that we've covered so far this year. It's quite a bit. We started with Chapter 4, beginning of semester 1, which was designing studies. We talked about sampling and surveys. We want to know how to sample. There's different ways we can do this. We can do a convenience sample, voluntary response sample. Both of those usually result in some sort of bias. Even better would be doing random sampling, which we have a simple random sample, which we refer to lovingly as the SRS. And we have a stratified random sample, cluster sample, as other types of random sampling. We always need to consider types of bias, which could be undercoverage, non-response, or other types of response bias, such as question wording, for example. Experiments. Observational study versus an experiment. What's the difference? An observational study is simply observing something that happens and recording what you saw. An experiment is purposeful. You're purposefully putting a treatment on some group of individuals or on an individual to see what happens. Right? We have treatments, experimental units, and subjects. Treatments are the things that you're doing to your subjects. The experimental units is the smallest unit of subjects that can receive an individual treatment. Depends on how you set up your experiment. Tells us what the experimental units will be. We talked about how to experiment well. We need to use random assignment, comparison, control, and replication. Those 4 things are all part of a well-designed experiment. When we want to use a completely randomized design. We need to be aware of the placebo effect, whether or not we want to set up a double-blind or a single-blind study, and then if the results are statistically significant, which we can now actually do the math for after chapter 9. We can use a block or randomized block design, and a form of block design is our matched pairs design, which then leads us to using matched pairs T procedures, which is a form of one sample T procedures, which could be used for confidence interval or a significance test. And then we always want to be aware of our scope of inference. What can we actually make a conclusion about? Can I make a conclusion about the larger population? Can I only make a conclusion about the types of people who participated in my study? Right? We need to be able to make that call based on our experimental design. Just a quick little graphic on the difference between SRS, stratified sample, and a cluster sample. Our SRS is simply randomly selecting people from the group, whether we use a random number generator and assign everyone a number. We roll a dice, we put everyone's name in a hat and randomly select them. It's random sampling. A stratified sample is when we separate people or individuals or whoever we're studying based on commonalities. So we group people together based on common characteristics, and then we randomly select people from those strata. A cluster sample. One moment, please. Someone's waiting in the lobby. There we go. All right, a cluster sample is when we group people together based on location, like they're close to each other. So we're going to group them together, group everyone together. Then we randomly select which groups will participate in the study. Everyone in a cluster must participate. You don't select people within a cluster. If you're selecting people within the group, that's then stratified again, different type. All right. Our random design, our completely randomized design can be shown in a kind of arrow diagram here. We can start by randomly assigning students to a treatment. We have 2 groups, right? So we randomly assign students to group 1 and group 2. We can do that by rolling a dice or just randomly numbering them off 1, 2, 1, 2, 1, 2, 1, 2, whatever, right? And then flip a coin to decide who gets treatment A, who gets treatment B, and then compare the results. That is a completely randomized design. A form of completely randomized design would be our block design, where we group students first by grade level, right? And then they randomly get assigned to group 1 or group 2, and then we randomly assign which treatment goes to group 1 or group 2 within each block, and then we compare the results. Another form of a block design would be our matched pairs design, right, where each individual or each pair of individuals becomes a block, and then each individual may get both treatments at different times, and that time is randomly selected, right? Or each pair of individuals, it is randomly assigned which of these 2 similar individuals will get a certain treatment. And then ultimately we compare which was more beneficial between that for that individual or between the 2 paired individuals, and we get a single result, which is why we use a 1 sample T procedure for that result. Chapter 1 went into exploring data. Right? We have to make sense of our data. Right? We have individuals and variables. Right? We have categorical variables and quantitative variables, and then we can display those in distributions. Remember, categorical data or categorical variables represent categories. Categories could be colors, right? Race, male or female, left-handed or right-handed. Those are categories. It doesn't make sense to calculate an average for the category left-hand and right-hand. We can't add L and R together and divide it by 2. Quantitative variables are things that we can logically calculate an average for. And that's kind of the big differentiation. I can sometimes have numerical values attached to categorical variables and kind of move them into being a quantitative variable depending on how we display them. But that's all different things. Our categorical data can be displayed in bar graphs, pie charts, two-way tables, which we can then use to make marginal distributions or conditional distributions, and determine association. Quantitative data is displayed in dot plots, histograms, stem plots, back-to-back stem plots, split stem plots, and we always can determine the shape, center, and spread and possible outliers of quantitative data. Right? We cannot determine the shape, center, or spread, or outliers of categorical data. Bar graphs or pie charts don't have outliers. Their shape can be changed based on the arrangement of the variable. Right? So they don't have those things. The distributions of quantitative data can be symmetric or skewed. Right? They can be skewed right, skewed left. Remember, the direction of the skew is the direction of the tail. Whichever direction the tail points, that's the direction of the skew. They can be unimodal, bimodal, or multimodal. When we describe quantitative data, we must describe the center, mean or median, the spread, range, IQR, standard deviation, whichever one kind of makes the most sense. Right, we have our shape, which we said in the previous one. We want to be able to identify possible outliers. One of our best strategies on that is using the 1.5 times IQR rule. And IQR again is the interquartile range, the space between Q1 and Q3. Box plots are used to show that 5-number summary of minimum, Q1, median, Q3, and maximum. And the box is the IQR. And this is in my way now. And we can use these things to compare distributions. Here's a look at a pie chart and a bar graph used to represent categorical data. We also have a two-way table showing our categories, male, female, and SUV versus sports car, and then the tallies or counts or frequency of each of those things based on those categories, and our marginal distributions on the right-hand side in the bottom of that chart. When displaying quantitative data, we can use a box plot, a histogram, a stem and leaf plot, or a dot plot. Right? The major difference between a histogram and a bar graph is that a histogram, the bars touch. Where one bin ends, the next bin begins. Each bar has to have the same width. Right, in this example here, it's 1 through 5, 5 to 10, 10 to 15, 15 to 20. Right? The first bin goes from 1 to less than 5. The second one goes from 5 to less than 10, then 10 to less than 15. Right? If by chance we don't have data in one of those categories, then there wouldn't be a bar there, and then we would have a space. Otherwise, bars touch. We have chapter 2 of modeling distributions of data. Right, we want to be able to describe the location in a distribution. We can do this with percentiles, the cumulative or relative frequency and standardized score, or z-score, which is a form of transforming our data. Right? Taking an original score and then standardizing it is transforming it. We use density curves and normal distributions. Right. A density curve has an area of 1 under the curve. The mean and median of a density curve, if this is mean and median of a density curve, are in specific location based on whether or not that it's symmetric or skewed. In a symmetric curve, the mean and median will be in the same place. If the curve is skewed to the right, the tail will pull the mean away from the median towards the right. If it's skewed to the left, we get the opposite result. Right, we have our normal distribution, which is represented with n parentheses mu comma sigma, where mu is the mean and sigma is the standard deviation of that population. Right, and they completely describe the normal curve that represents that data. There's the 68, 95, 99, 7 rule. The standard in our standard normal distribution, we will use a lot of table A, which we've seen throughout the course, and we use all of these things to make comparisons using z-scores or standardized scores. We can perform normal distribution calculations by finding the proportion of a curve based on a given value, or finding a value given a percentile or proportion of a curve. Meaning we can work from a original value, standardize it, and then find the proportion under the curve less than that value or greater than that value. Or we could start with a proportion under the curve greater than a certain z-score or less than a certain z-score, unstandardize that, and get our original score. Right. We can also assess normality by checking to see if it's approximately symmetric in bell shape and close to the 68, 95, 97 rule. Or we could use a probability plot on our calculator. Here's a quick picture of that 68, 95, 97 rule. All right, showing that 68% of the data is between 1 standard deviation of the mean, or in this case of 0, right? Standard deviations. All right, 95% of the data lies roughly between 2 standard deviations of the center, and 99.7% of our data is roughly between 3 standard deviations. All right, and then our standardized score, the z-score is found by taking your original value x, whichever value that is from your sample, minus the mean of that population divided by the standard deviation, and that gives us the z-score. We then use that with table A to find the proportion. We then get into a probability. I don't know why this slide does not like me. All right, there we go. So when dealing with probability, we started with randomness, probability, and simulation. All right, probability is always between 0 and 1 and describes the proportion of time a random outcome would occur in the long run. That's what probability does. Simulations can allow us to model long-run behavior and imitate chance behavior, which can be very useful if we don't want to spend the time it takes to actually go through all the simulation. We have some probability rules and definitions. We have sample space, the set of all possible outcomes. Right? For instance, if I am rolling 2 6-sided dice, right, and I'm interested in the sum of the 2 dice, there are 36 possible outcomes between the 2 6-sided dice. All right, our probability model would then consist of a sample space and probability of each outcome, meaning probability of the sum of the 2 dice being anywhere from 2 to 12. Right? The event, or an event, is any collection of outcomes from some chance process and a subset of the sample space. We could define event A as being rolling 2 dice and having it have a sum of 6 or less. Right? There's a certain number of outcomes that fit that event, right, out of the 36 outcomes. If all outcomes in the sample space are equally likely, which our example is, right, rolling dice, they are equally likely to land on any of the 6 sides between the 2 dice. Probability that event A occurs is the probability of A equaling the number of outcomes in event A divided by the total number of outcomes in a sample space. And 2 events are mutually exclusive or disjoint if they have no outcomes in common. Right? 2 disjoint events would be saying event A is having the sum of the 2 dice be 6 or less, and event B being the sum of the 2 dice being 10 or more. There's no intersection between those two. I cannot have the sum of the dice be 6 or less and be 10 or more at the same time. It is impossible. There it goes. We also have our complement rule. That says that the probability of A complement is equal to 1 minus the probability of event A. So again, if event A is having the sum of the 2 dice being 6 or less, the complementary event would be the sum of the 2 dice being greater than 6. If I already know the probability of getting 6 or less, I subtract that from 1, and I have the probability of the complement. All right. And we have the addition rule for mutually exclusive events, so this only applies to events that are disjoint, meaning they have no outcomes in common. Probability of A or B, A union B, is equal to probability of A plus the probability of B. All right. We can use two-way tables and the general addition rule to help us with probabilities. When finding probabilities involving 2 events, the two-way table can display the sample space, making probability calculations easier. We can use the general addition rule for 2 events. If A and B are any 2 events resulting from some chance process, then the probability of A union B, or A or B, is equal to the probability of A plus the probability of B minus their number of events they have in common. And this is to avoid counting those events twice, which would throw things off. We can also use Venn diagrams to help determine probabilities by modeling sample space of a chance process involving two events. Remember, a Venn diagram is when you get the two circles, draw them both on a square, and they have a little intersection space between them. That can help us model two events. We also have conditional probability and independence. Right? The notation, probability of B given A, right? That bar in between B and A says given, represents the probability that event B occurs given that event A has occurred already. We write this as P of A given B equals probability of A and B divided by the probability of B. Essentially, whether we're doing the probability of A given B or a probability of B given A, the numerator will be the probability of their intersection, probability of A and B. The denominator, the value on the bottom, is the probability of the second event listed in the P of A given B, right? So in this case, it's probability of A given B, probability of B goes on the bottom. If it was probability of B given A, probability of A would go on the bottom. It's not like this slide. Let's go. Come on, there it is. Oop, too fast. I don't know why this presentation is not cooperating with me. Come on, PowerPoint. Don't fail me now. There we go. A little bit more in conditional probability and independence. We have the general multiplication rule, meaning the probability of A and B, right? Probability of the intersection of those two events is equal to the probability of A times the probability of B given A. Right? When chance behavior involves a sequence of outcomes, a tree diagram can be used to describe the sample space. Right? So essentially, if you're dealing with kind of like a choice process sometimes, and it's like, okay, or a random process where the next thing that happened depends on something else happening first, right? So maybe you have a tree diagram where it's like if the sum of the two dice is less than 6, you go up on one side of the tree. If it's greater than or equal to 6, it's the other branch, and then if the second roll has a sum of something or something, right? And we have all these branches depending on the sum of the dice. We can have something like that happen and demonstrate it with a tree diagram. When knowing that one event occurred does not change the probability that another event occurs, we say the two events are independent. When we have two independent events, the probability of A given B is equal to the probability of A, and the probability of B given A is equal to probability of B. If two events are mutually exclusive or disjoint, they cannot be independent. Meaning if they are disjoint, knowing that event A happens affects the probability of event B. Because essentially if I know event A happened, and those events are disjoint, I know event B didn't happen. So it affects the probability. If events A and B are independent, then probability of A and B equals probability of A times probability of B. Okay. Man, let's get, come on, go. So that leads us into chapter 6, random variables. We have discrete and continuous random variables. A random variable takes numerical values determined by the outcome of a chance process. Probability distribution of a random variable x tells the possible values of x and the chances that each of those values occur. Right. Discrete random variables have a fixed set of possible outcomes. So again, if we look at the sum of two dice that have been rolled, the random variable x could take the values of the sum of the two dice, and we have the possible values of 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Each of those outcomes has a specific probability of occurring. Okay. Continuous random variables take all the values in some interval of numbers. Right, meaning a continuous random variable can take any value between 0 and 1, meaning it could be 0.1, it could be 0.5, it could be 0.01, 0.1111, 0.2135. There's an infinite number of possibilities, hence continuous. You can take all the values in some interval. Right? If x is a random variable, the mean or expected value is the average of the values of x, which we write notation mu of x equals the expected value of x equals the sum of each observation times its probability, right? Which is first observation times the probability of that observation plus the second observation times the probability of that observation, and so on until we run out. The variance of a random variable, x, is sigma squared x, equaling the sum of the difference of the observation minus the mean squared times the probability of that specific outcome, x sub I. I think that should just be mu. And then the standard deviation is the square root of the variance. We can transform and combine random variables. If we add or subtract a constant to a random variable, it increases or decreases measures of center and location, which would be considered the mean, median, and percentiles and things like that. It will have no effect on shape or spread. Okay. Multiplying or dividing a random variable by a constant multiplies or divides measures of center, location, and spread. Right. So this, in addition to mean, median, and percentiles, adds on that it affects IQR, range, and standard deviation, but again does not have effect on shape. We can transform and combine random variables. Right. If x and y are any two random variables, then the mean of the sum of those random variables, x plus y, is equal to the mean of x plus the mean of y. And the mean of the difference of those random variables is the mean of x minus the mean of y, which we've used in chapter 10. If x and y are independent random variables, then the variance of the sum of x plus y is equal to the variance of x plus the variance of y, and the difference of the variance of the difference of x and y is equal to the sum of the variance of x plus the variance of y, which this, again, we used in chapter 10. And finding the standard deviation of the difference of two populations. We can also use binomial and geometric random variables. These have specific cases that they get used in. We must have a binomial setting to use a binomial random variable, and in this case, to check for binomial setting, we have to check our bins. Right? The variable must be binary. It's either a success or a failure. Needs to be independent, so knowing that the first thing was a success does not affect the next thing having a success. Right? We have to have a specific number of trials that we're running, and the probability of success must be the same for each trial. Right? If x has the binomial distribution with parameters n is the sample size, or the number of trials, and p, probability of success for each trial, the possible values of x are the whole numbers 0, 1, 2, up and up and up till n. Right? The binomial probability of observing k successes in n trials is the probability of x equaling k, which is equal to n choose k. That's what's in the parentheses there, that n on top of k. It is not a fraction. Right? There is no fraction line. It's n choose k, which is basically saying how many different ways can I have k things happen in a set of n possibilities. Right? Times p to the power of k, the number of successes, times 1 minus p times n minus k, which n minus k would be the number of failures, and 1 minus p is the probability of a failure. The mean and standard deviation of a binomial random variable x are mu sub x equaling np and sigma sub x equaling the square root of np times 1 minus p. For a geometric random variable, we need to check for a geometric setting. This has repeated trials of the same chance process in which the probability p of success is the same for each trial, just like with a binomial. However, the goal is to count the number of trials it takes to get one success. The binomial is measuring what's the probability of getting a certain number of successes in a set number of trials. Geometric does not have a set number of trials. If y has a geometric distribution with probability of success p, the possible values of y are the positive integers 1, 2, 3, and so on up to infinity, which is why a final n or something is not listed there. The geometric probability that y takes any values is p of y equaling k is equal to 1 minus p times k minus 1, which would be the number of failures, times p, the probability of success, and there's only one success, so it's p to the first power. Right, the mean of a geometric random variable is mu sub y equaling 1 over p. Let's see, 208. Right, I still have time. So that leads us into chapter 7, sampling distributions. The sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the population. The sampling distribution of a sample proportion is as follows. If we choose an SRS of size n from a population of size capital N with proportion p of success, and we let p hat be the sample proportion of successes, then the mean of the sampling proportion of the sample, the mean of the sampling distribution of the sample proportion is equal to p. The standard deviation of the sampling distribution of the sample proportion is equal to the square root of p times 1 minus p over n. These results are only valid if the 10% and large counts conditions are met. We can calculate the mean, but the standard deviation is not necessarily valid if the 10% condition is not met, and we cannot perform any type of calculation beyond this if the large counts condition is not met. Large counts condition allows us to use normal distribution and normal calculations. We also have the sampling distribution of a sample mean. And in this case, we suppose that x bar is the mean of an SRS of size n drawn from a large population with mean mu and standard deviation sigma. So again, I know the mean and standard deviation of the population. Then the mean of the sampling distribution of the sample means is equal to mu. And the standard deviation of the sampling distribution of the sample mean is equal to sigma divided by the square root of n, or the sample size. The standard deviation is valid if the 10% condition is met, and we can only use normal distribution calculations if the normal/large sample conditions are met. And again, that's saying that the sample was drawn from a population that is known to be normally distributed, or we have at least 30 individuals in our sample. Sample size must be at least 30. Otherwise, we would have to graph all of our data and see if the sample was in fact normally distributed, or at least it's not skewed strongly or having outliers. So then we get to chapter 8. Interpreting confidence intervals and confidence levels. All right, chapter 8 is confidence intervals. To interpret a C% confidence interval for an unknown parameter, we say we are C% confident that the interval from blank to blank captures the parameter in context. Right? The true proportion or true mean of people who like this certain thing, blah, blah, blah. Right? To say we are C% confident is shorthand for if we take many samples of the same size from this population, about C% of them will result in an interval that captures the actual parameter value. These two things are answering two different questions. If you're asked to interpret the C% confidence interval, right, so your conclusion, we are 95% confident that the interval captures the true mean, true proportion, that's one thing. If you're asked to then interpret the confidence level in context, right, that's the second thing here. we can calculate a confidence interval. Right? The confidence interval for estimating a population parameter, proportion or mean, has the form statistic plus or minus critical value times standard deviation of the statistic. And sorry, that became off center there. The margin of error is the critical value times the standard deviation of the statistic. So everything to the right of the plus or minus sign is considered the margin of error. When we're estimating a population proportion, we must first check the conditions: random, 10% when sampling without replacement, and large counts conditions. Then we use the one sample z interval for a population proportion inference method, which gives us the interval p hat plus or minus z star times the square root of p hat times 1 minus p hat over n, right? Where z star is the critical value for that standard normal curve with c% of its area between negative z star and z star. And again, we have to use, like, what's the confidence interval, what percent, split that between the two tails, and do all that fun stuff to determine what the z star value is. When constructing confidence intervals, always use the four-step process: state, plan, do, and conclude. All right. Same thing goes for when doing significance tests: state, plan, do, conclude. To determine the necessary sample size for a given c% confidence interval with the maximum margin of error ME, solve the following inequality for n. And again, this is a maximum acceptable margin of error, which is why we have the less than or equal to inequality. So we would have a value for z star, we would have the value of p hat, we just don't know what n is, so we put in the missing variable values that we know, solve for n. Right? And in this case, the margin of error will be a percentage that's transformed into a decimal. Okay. We can also estimate a population mean using confidence intervals. And again, we have to check our conditions first: random, 10% when sampling without replacement, and normal large sample. Right? Then we use the one sample t interval for population mean inference method. That is x bar plus or minus t star times s sub x, the standard deviation of the sample, divided by the square root of n, where t star is the critical value for the t n minus 1 distribution, meaning degrees of freedom, right? Which is based on the sample size. 1 less than the sample size gives us our degree of freedom, with c% of its area between negative t star and t star. And again, on our t distribution, we look across that bottom row, right? And find the percent, and then intersect that with the degree of freedom line, and we get our t star. Again, we must do the four-step process: state, plan, do, conclude. Determine a necessary sample size for a given c% confidence interval with a maximum margin of error ME. Solve the following inequality for n. Again, we have z star, right? We do not use a t statistic in this case. We use z star and the following percent confidence interval. Even though this is a mean, and we typically use t and stuff for that, in this case we use z star because we don't know the degree of freedom. So we can't use the t distribution, right? Sigma divided by square root of n, less than or equal to margin of error. In this case, because we're dealing with a mean, the margin of error is a number, it is not a percent. Right, so if your acceptable margin of error is to be within 2 units of something, then the margin of error is 2. It's not going to be 0.2. It's not going to be based on the confidence interval. We're going to stop here, I think, because, yeah. All right, so obviously we didn't get through everything, but that's okay. All right, so again, I didn't think I was going to be able to get through all of it. There obviously is chapter 9 and 10 stuff in here still. I highly recommend checking out the rest of this. It is in the things you might need module in Canvas. And it's the PowerPoint presentation, so it goes through with all the animations and stuff if you download it. And If you have questions, please let me know. This is just meant to be an aid and you guys looking back at all the stuff that we've covered so far because it's a lot. Just kind of like jog your memory of all these things. Tomorrow we'll be doing the short practice demo in the AP testing app. If you don't have that, then I'll have something else for you to do. Because I think 45 minutes is enough to do that. And then next week we will start on our essentially final unit of everything, which is going to be a combination of chapters 11, 12, and 3. Which also means you will only have one more multiple choice assessment and one more free response question self-assessment, right, for the semester. Right, so rather than having 3 more, because there's 3 more chapters, we're just going to push it all into one and have 1 more, just to make it a little easier. Okay. If you have any questions, comments, or concerns, please ask. Let me know. This went really, really fast. Other than that, I hope you all have a great rest of your day, and I'll see you at the same time tomorrow.